next page.
Wait, I need to announce again. So sorry for the technical glitch. We are happy to have Balt van Rees from Ecole Polytechnique tell us about the Navigator function for the conformal Bootstrap.
Thanks. So yes, what I wanted to, so let me restart from the beginning. I'm going to talk about this paper that appeared less than a month ago with the same name as the title, same name as the title of my talk, written, as I said, by Benoit, PhD students, two postdocs, Ningsu and Martin Rehorst, Slava and David, as you know, and others. That is the usual thing with the 6 author papers, that it cuts out after 5 authors in on many websites. But it's a 6 author paper, so you're only missing one. So this is the problem. I hope you can still see my screen. I'm just starting from the beginning. So the problem, as I said, was numerical bootstrap problems nowadays come with many parameters attached. So with parameters, I mean external scaling dimensions like deltas and OPE coefficient ratios that I call alpha here on this slide. So let me briefly remind you what these alphas are, where they come from. An example would be, for example, if you analyze these kind of 4-point functions and you have an operator of type 2 being exchanged, then in this 4-point function, it comes with coefficient C112 squared. In this 4-point function, it comes with C222 squared. And here in this 4-point function, it comes with C112, C222. But that means, of course, there's a relation that I indicated here in green, which is that the product of these two coefficients should equal to the square of these coefficients. But that relation makes the problem not convex, imposing that relation. And it's not something that STPB can handle in one go. So instead, what you do is you set C222 equal to alpha times C112, where alpha is some coefficient, and you just scan over alpha, which here is some element of RP2. But you can imagine in multi-correlator setups, there are similar relations you have to impose. They're more complicated relations. You have more angles, and you have a higher real projective space that you have to scan off. So the problem is not convex in these alphas, and the problem is not convex in the external scaling dimensions deltas. And that means that you basically have to scan over these what I call parameters. And these parameters nowadays can get huge. So for example, here are 2 interesting problems that one can try to attack that might be interesting for various physical reasons. The O3 model with not just the vector, the scalar, and the tensor, but also a 4-index tensor. Then you get 4 deltas, obviously, but you also get 9 OPE coefficients. Similarly, for easing, you would have, if you want to do analysis involving sigma, epsilon, and epsilon prime, you have the 3 deltas, but you will find that you have 6 OPE coefficients. So, and these are big spaces. And normally, in the traditional methods, if you want to carve out an island in this space, well, how does it work? You've all seen these very nice plots where you have some islands in some space of, say, scaling dimensions. But what happens in reality is, of course, that for each, these islands consist of basically a very fine grid of points if you zoom in. And for each point, if these axes here were scaling dimensions, then for each point, you would have to do a search over the angles involved. So a search over the RPN or multiple real projective spaces. So that, of course, takes time. I've introduced, well, let me skip that. So, or actually, I can do that. So the real projective search takes time in some sense. It's a little bit less expensive than the searching over deltas, because you can do the following. You can pick a direction in this real projective space. If you can solve crossing symmetry, in other words, if there's no functional, then you just mark the point green, because then you're done. If you find a functional and you excluded that particular direction in the real projective space, one of the tricks that you can use is that you can recycle this functional to exclude the bigger subset of this real projective space. So you carve out a chunk of this real projective space, and if there's anything left after carving out this chunk, then of course you have to restart, pick a new direction, and so on. And if there's nothing left, then you can mark the project. But you see, so even in this real projective space, you don't have to, you can carve out big chunks at a time, but there's still some iterative process. And in the end, you're left with, often for all the green points, you're really left with a direction in real projective space that is suitable. In other words, with a solution to crossing. So this is the method as it traditionally works. There's some advantages, some disadvantages. So for example, the method is very robust. You really carve out the island, and there's a very detailed picture that you get of the allowed space in that. Another thing that's a bit of a technicality for those who know is that you can hot start. So you can take the results at one particular point and use it as a starting point for the next point, and that speeds up the process significantly. But there are two important downsides, and those are the downsides we want to address. So first of all, it needs a feasible point. In order to even begin your islands, you need your search like this, where you have red points and green points. It's easy to find points that are excluded generally. So generally you have your delta space and you have a lot of green points in it. But of course you need to know a little bit better where the island is. So you need at least one red point in order to start refining the island. And just finding this one red point in practice can be very difficult because, and in some sense very cumbersome, because you need some idea of where in OPE space or where in scaling dimension space you have to be in order to find at least one feasible point. So this is a very hands-on process, and already for that reason it's just annoying, and it would be nice to eliminate it or automate it. And then another disadvantage is that it's just a very cumbersome method in general, because as this RPN search shows and this picture shows, you really get an island in the full parameter space. So if you have a 13-dimensional parameter space, you would get a rough idea of an island in a 13-dimensional space. But you cannot plot such a 13-dimensional island. And so you have to project that 13-dimensional island down to the information you actually want to know. So for example, to 3 dimensions or 2 dimensions, if you want to put nice plots in your paper. Or if you want to put something in the abstract, you put some numbers in the abstract, that would be effectively a projection down to 1 dimension, where, for example, you plot along the horizontal axis, you project along the horizontal or vertical axis, and then you say, this is the interval of scaling dimensions. If this would be delta sigma horizontally and delta epsilon vertically, you would say, this is the window in which delta sigma must live. So you get too much information in some sense from this traditional method. So this is then the method that we propose, and it's not so difficult to convey the main point. We define, so we take this parameter space, which I here sketched as a 3-dimensional parameter space, and I took 2 scaling dimensions and 1 OPE angle. So the picture is whether we unify this parameter space. We don't distinguish between the different types of parameters. And on this parameter space, we define some function, curly n of p, that we call the navigator function, and p are here the parameters, such that it has the following properties. First of all, we want the navigator function, the sign of the navigator function to tell us whether we're inside the island or outside. So it's negative if feasible, if there's a solution to crossing, and it's positive if it's infeasible. And then ideally, we want also this function to be smooth and grow very, very large when it's very infeasible. So when you're very far away, the function should become very positive. And then we want it to be smooth because, well, for reasons that we'll see in a minute. So then what happens? How did we then solve the 2 downsides of the traditional method? Well, first of all, there's no need to initially find a feasible point because this navigator can do it for you. That's why we called it a navigator function, because it navigates towards a feasible point. The idea is just you start in any point, and then with a smooth function, you can use standard numerical minimization algorithms to start going down to start moving in parameter space such that the navigator function decreases and decreases and decreases until you hit the negative point. So I'll come back to these algorithms, but they're basically Newton type algorithms are the ones that we use or that we propose. So the feasible points can be found by using this Navigator function, and you don't need it a priori. You don't need to look at, say, Monte Carlo data or data for lower derivatives or from other systems to get one feasible point. That's what the method does for you. And secondly, the method is a lot less cumbersome, precisely because we don't have to scan over this full map out an island in this full 13-dimensional space. Say. So for example, if I want to know the upper allowed value for delta 2, say, so this projection down to 1D that I talked about in the previous slide, well, we just have another optimization algorithm, which is to maximize delta 2 over, say, the parameter space P, such that the Navigator function is negative. And this is also a method you could easily attack with Newton type methods, and it'll just move you exactly to the tip of the island right here, exactly the maximal value of delta 2 that you want, very, very quickly without having to map out the entire island. So here's then the plan for the talk. It's again fairly straightforward. So first of all, we have to find the Navigator function. Then I'll tell you a little bit about the minimization techniques that we propose for this Navigator function. And then I'll show you some initial results of some example island finding problem that we put in the paper. So, okay, this is all good and well, but can we really find such a nice Navigator function NLP? Does such a Navigator function even exist? Oh, I must say, I'm going to use the term Navigator function because we're in this, I don't know, like we're talking about these geographic features all the time, islands, peninsulas, all of these things. And so we thought the Navigator function name was appropriate in that context. But it must be said that this is also in the mathematical literature fairly similar, if not equivalent to what's called a level set function for the feasible set. So if you Google level set function, you find that functions defined like that have very similar properties to what I just wrote. So can we find a nice Navigator function? Well, here is a simple non-answer, which nevertheless may be instructive to show you that the problem of finding a nice Navigator function is not entirely evident. So suppose you do a standard Bootstrap problem. Sigma times sigma has an OPE where there's the identity, then epsilon, and some, say, irrelevant stuff. And so epsilon is an isolated operator, and we can try to maximize its OPE coefficient, lambda sigma sigma epsilon squared. And let's propose that minus the maximum OPE coefficient is the Navigator function. So indeed, if this thing is positive, you find a nice finite upper bound on the OPE coefficient, then there is a solution to crossing. And so the Navigator function is negative in the feasible region. And similarly, if there is a solution to crossing, then almost always there's a nice finite upper bound on the OPE coefficient and the Navigator function is negative. So there's small subtleties because in some cases there's no upper bound on an OPE coefficient, but it's really not worth spending time on. Also, there's also a nice property that if the upper bound on the OPE coefficient comes out negative, well, you have an upper bound on something positive and your upper bound is negative. That cannot happen. So there must be no solution to crossing. But the problem is here that this arrow here points only in one way. So if there's no solution to crossing, that doesn't mean that there's a finite negative upper bound. So in practice, you see something like this. Inside the island, you get a nice positive upper bound. Then this thing goes down. And then it goes down further. And then it becomes minus infinity. And the problem is no longer well defined. And in practice, what happens is, we can explain this divergence a little bit. What happens is that if you think about how functionals work and how the optimization procedure works, is that the moment you find this divergence is precisely the fact that precisely originates from the statement that there does not exist a solution to the crossing symmetry equation, even if you allow this OPE coefficient squared to be negative. And then there is, so you see that we're sort of relaxing the crossing symmetry equations a little bit. We allow this guy to be negative. And that allows us to find the finite value here, slightly outside the island. But the moment you allow this guy, the moment there's no longer a solution, even if you relax this with this relaxation, that's when you get minus infinity. And in this context, I should mention that Nevertheless, this can be a good navigator function if you really want to very precisely map out the boundary of the island. And because then you're just very, very close to this edge, and then everything is perfectly fine. And this is the kind of thing that was, for example, done in the paper that is cited here at the bottom. So that was the non-answer. And that shows that the problem is not entirely obvious. At least it wasn't to us. Maybe it is to you. So here's what we propose as a solution. So we can find a nice navigator function if we make sure that the primal problem, the solution to crossing, can always be solved. So we have the solution to crossing, and now we're going to relax it in such a way that it can always be solved. So you can do, for example, something like this. So suppose you have some standard crossing equation. You have an identity operator. You have some blocks minus. Of course, these are blocks minus blocks minus cross blocks. So you want to know if there's a solution to this thing without the extra term. So our claim is that you can then do something like this. So suppose that you add some extra term that we'll have to define, and we'll do so in a second, such that there is always a solution to this equation with positive OPE coefficients and the spectrum if you assume, as long as this coefficient mu here is equal to 1. Then our claim is that we get a nice navigator function if we try to minimize this coefficient mu, subject to, of course, the fact that this crossing symmetry equation must be obeyed. So this is our claim for a navigator function. So I repeated it here. A navigator function proposal is minimize mu subject to the solution of crossing symmetry. So you see, sort of with mu equals 1, you can always solve it. So you generally are going to get an answer mu slightly less than 1. So it's the sort of mu is like a measure of the amount of extra stuff that you need in order to solve crossing. So indeed, what if your minimum comes out negative? So your navigator is negative. Then, well, you know there exists a solution with negative mu, and there exists a solution with mu equals 1. So you can take a linear combination, and then you should see that there's actually also a solution with mu equals 0. And so that means that is basically the statement that it's feasible. There's a solution to crossing symmetry in general. And so if you negate this statement, you see that the infeasible region, the navigator function, is indeed positive. Furthermore, our navigator function is guaranteed to be bounded from above because it's less than or equal to 1 always. Because there's always a solution with mu equals 1. So let me remind you of the picture that I wanted. There's a negative region in the feasible, it's positive in the infeasible region. And of course, we want it to be very, very positive, very far away from the feasible region. Now, okay, here it's bounded by 1. But if we know that it's bounded by 1, we might as well do some kind of transformation. We set n tilde to be n over 1 minus n. And you see that if n approaches 1, then n tilde blows up. So you can simply do these very simple transformations. And you see that n tilde is actually much, much bigger than 1, as long as n goes to 1. So the fact that it's bounded from above doesn't really mean any. It's not fundamental for us. We can make it as large as we want if we do this kind of simple transformations. And of course, this is the semi-definite programming problem. As many people here would probably know, this is just an OPE coefficient, very much akin to an OPE coefficient minimization problem, right? You have some stuff in the crossing equation, you try to minimize its coefficient. And indeed, we all know the sort of dual formulation of this, where we say, well, the functional alpha needs to be positive on all of these blocks. We normalize alpha.m to be equal to -1. And then you see that alpha.1, alpha acting on the identity operator, gives you a lower bound for mu. And so to get the best lower bound, you have to maximize alpha acting on the identity operator. And that's the dual problem. Yeah, so there's a question in the chat if there's a sense in which we are really far away from the solution if n is closer to 1. Indeed, that is the hope. so the hope is that this function is negative here and gradually grows the further and further you are from the solution to the crossing equation. Whether that is realized in practice, well, I'll show you some plots and there it's realized, but it's realized in full generality, I'm not entirely sure. So now I have turned the problem of finding a navigator function into the problem of finding a function m such that this solution, this equation always has a solution if I set mu to equal to 1. So we found 2, maybe 3 such functions, m of z. First one we call the sigma navigator function, where m is just a whole bunch of blocks with negative coefficients. Because if you add this term, that's affected with some fixed negative coefficient that are just large. If you add such a term, then of course, this term can make the coefficients positive again. And if you have sufficiently many blocks in your equation, you can basically see that this extra term allows for a whole bunch of OPE coefficients to become negative. Right, all the terms, all the blocks in this sum P can have a negative OPE coefficient. And then there's some generosity argument and some fact that that also relies on the fact that you only check finitely many crossing equations, and here you're adding finitely many vectors. That shows that if you have a sufficiently large but finite number of blocks, this will generally work in the sense that this equation can always be solved. So it's just a relaxation of you should think of it as a relaxation of OPE coefficients to become negative. So that's one option. This is the other option that we'll look at today, which we call the GFF, Generalized Free Field Navigator. And it is just it's just based on the realization that this equation always has this, there's always a generalized free solution to Gaussian. So if you make some assumptions about the spectrum and those assumptions exclude certain conformal blocks that should be part of the generalized free field solution, well, then we just add them by hat in M. So we add just the missing blocks with the right coefficient such that the generalized free field solution can be found here. And then, of course, generalized free field is always a solution not just to single correlator problems, but also to multi-correlator problems. It always works. So there's always such a generalized free field navigator function. Right, and if you have some isolated blocks here, then in general, their coefficients can be, their coefficients, you just set them to 0, and then it gets replaced by the generalized free field solution. So those are 2 relaxations of the crossing equation that you can use. And today we'll look at the GFF navigator. It's very natural, I think, because it just adds a few blocks. There's no choice about the kind of blocks you have to add. There's a natural normalization also. So it's a nice navigator function. But in fact, you can even dig a little deeper and open the semi-definite programming box. And then you will find that you don't really have to work at the level of the crossing equation. You can just work at the level of the primal and the dual problem and the semi-definite matrix that underlies the whole numerical algorithm. And one of the things you can do is replace a matrix that's typically called X. If you don't know what it is, it doesn't really matter. As the semi-definite programming problem is always involves this matrix X that's required to be positive semi-definite. And if you cannot find such an X, then you're out of luck. And our proposal for relaxation is just to say, well, you just take X and you add the multiple of the identity. Then you can always find a positive semi-definite matrix if you make mu large enough, and then you can minimize mu. And so this is the kind of relaxation that you can do for a general semi-definite program, even if it doesn't come from a numerical conformal bootstrap problem. And so, for example, if you want to do S-matrix bootstrap or other things, and you want to use the navigator function, then this relaxation of the primal problem might be the way to go. So, okay, the GFF Navigator is the thing we want to look at. Well, a picture, as they say, says a lot. So here is a picture of a GFF Navigator for the easing island, basically. So there are, in principle, 3 parameters in this problem. This is really the standard sigma and epsilon 3 correlator problem. So the parameters are delta sigma, delta epsilon, and an OPE angle, theta delta sigma epsilon, and it is defined like so. So it's just the ratio of these OPE coefficients. So that's the angle I was talking about before. And this is the generalized free field navigator. So you add a couple of blocks corresponding to the generalized free blocks that are relevant in this, so that lie below the gaps. And then you find a function that looks a little bit like this. So here is a heat map where the value of the function corresponds to the contour, and this is the same function, corresponds to the color, sorry. And here on the right, you see the same function plotted in 3 dimensions. So this navigator function, and here delta epsilon, delta sigma. And so what do we see? Well, we see a smooth function. That's nice. We didn't have to have a smooth function, I think, a priori. It's probably expected on physical grounds, but the fact that it comes out smooth is nice. We also see that the minimum is unique. Well, you don't quite see it here, but at least you can see, so this white region here is a bunch of excluded points where the navigator function is negative. We've computed the value here, but just to illustrate where the island lies, we've just taken those points to be white. And so you see that, so inside this island, there's a unique minimum, but what you also see is that there are no other local minima elsewhere. So at least not for the range that we've plotted here. So that's, of course, great for optimization, because if we want to minimize this function, we're not going to be stuck in a local minimum. Whether this is the case more generally is not something that we can prove, but this is at least a very encouraging result, and I have no reason to believe that it's very different in general. Now, I must say this is just one plot, and there are you can slice and dice this 3-parameter space in different ways. So you can fix delta sigma and have a delta epsilon theta sigma epsilon plot, or doing all kinds of 2-dimensional cross sections. And in all cases, we find something that looks, roughly speaking, equally nice. So there's a unique minimum. You find plots that have exactly the same qualitative features. It's smooth. And so on, and we don't foresee any problems with the optimization algorithm. So that's our proposal. We have a navigator now, so we need to start minimizing it. Let me pause here and see if there are any questions at this stage or comments.
Hi. So how do we compute this navigator function at each point, like practically? Like, isn't that itself a minimization procedure?
Yes, but it's a standard semi-definite programming problem. So it's something you can do with the standard numerical Bootstrap tool called SDPB. So this is something you can code up. You can give it to this program called SDPB. It runs and it'll give you the answer. It is a minimization problem in itself, but it is completely within the realm of things that we've done before.
Okay.
So in that sense, it's a bit similar. So one of these runs is similar at some level to finding, one of these points if we ignore the RPN search. So it's like a step here. So finding a functional or finding a solution to crossing. And here, of course, you have to repeat it many times. But you have the advantage that you can terminate earlier because you don't have to optimize something. You just have to check for red or green, and you can recycle the results from previous runs. So it's faster here to find points, but roughly speaking, it's one run of the program, and the same for the value of the navigator function. That's one run of our standard program.
Balt, could I please also ask a question? So in your plot, if you go sufficiently far to the right, there's another allowed region there, right?
Yeah.
And do you know if the minimum of the function in that region is significantly smaller than the minimum in the inside the island?
I don't know. That's actually a nice question. Yeah, I should have drawn that thing, and of course, I had some plan of drawing it on the iPad. But yeah, there is another wide negative region here far to the right. Now, your question is whether it's more negative, or maybe the question would be like whether you're attracted more to this other island than to the island that you actually care about.
That's correct. Yes. I mean, how well do I need to know where to look?
Yeah, exactly. So I think, of course, there will be. We haven't checked the actual value, or at least I don't know it. Maybe people checked. I think it's important to say that indeed there is a region. If you're too far here to the right, probably outside the range of this plot, then you start minimizing and you go the wrong way. You go to outside you don't go to the easing island, you go to the continent. And that might be a problem in practice. I think, I mean, if you look at the advanced numerical searches, people have a rough idea of where the island is and also where the continent is. And so what we propose in practice is just to say, well, the user should put a hard cutoff somewhere and say, I don't want to look at the continent out there. So you should have a very crude picture of where the island is, at least.
But at some point, won't it minimize to negative infinity? Because if you literally go to the GFF point, you can just sort of trade between the OP coefficients and mu. So you can make it negative as you want by cranking up the OP coefficients.
Yeah, it might be negative infinity, but at that point, you've already found the island. So that is right. If you are one of the problems I proposed was to say, look, you want to find an island, you have this huge space and you want to find at least one feasible point. You just iterate until you find the negative point, and then you're done. And then if you iterate further, you might find negative infinity. In general, I think that is not generally at that point, you probably want to stop anyway, because I mean, you know that if your parameters were such that the generalized free field solution was a solution to crossing, then why were you doing numerics in the first place? Right, because you already know that there's a solution to the crossing equation GFF. So, but there might be other points where it's negative infinity, but I think it's a very minor problem. It's either GFF or maybe some solutions without an identity or so. I don't think they matter much in practice, but in theory, yes. We don't have a lower bound in the Navigator function.
No.
I mean, I suppose you could imagine being interested in a regime close to GFF, but not exactly GFF, and then you might worry more.
Perhaps, yeah, if you're very, very close. I don't think so, though. I'm not sure it's even close to GFF. I'm not sure it can go to minus infinity very easily.
But it has to be mentioned that the Sigma Navigator doesn't suffer from this problem, or it's well-defined and finite even near GFF. So if somebody needs to study that region, they should just use the Sigma Navigator.
That's true. Yeah, thanks. But yeah, so for example, if there are solutions without an identity operator, I think then you're lost. But
actually, I mean, Balt, you're probably not going to talk about Sigma Navigator much, but I should mention that there was a nice talk by Ning at the Bootstrap program, which is recorded, and there Ning talked about the Sigma Navigator very nicely. So if people are interested in the Sigma Navigator, they should watch that talk.
Thanks. All right, any other questions? See nothing in the chat.
Yeah, one other quick question. Do I understand correctly that the typical value of this Navigator function is order 1?
Yeah.
In the region away from that's not allowed. It's just order 1.
Yeah, between 0 and 1, right, by definition. But like I said, I prefer to map it from 0 to the positive real line, not negative real line. It's great if a navigator, right? You're gonna want to descend, and if a function is almost 1 everywhere, then it's almost flat, and that's not a great function to numerically minimize. For 1, it's not convex. So, but this fractional linear transformation that I propose makes it convex, or can make it convex. And if it doesn't, I mean, you can add some, change it a little bit. It'll generally become convex.
So when you said at the beginning of the talk, much bigger than 0 means it's you're far away from the allowed region. That means close to 1.
Yeah, here it's close to 1 for the function we proposed. But if I define this n tilde, then it becomes huge, because close to 1 becomes huge.
Yeah, thank you.
And so n tilde is really the function we should minimize. And in practice, that's what we've done.
Got it.
Any other questions? Okay, so let me talk about minimization techniques, or alternatively, I should say navigating. So for navigating, for minimization, any function in a parameter space, of course, it's hugely important to have a gradient. If you don't have a gradient, you just sample points, and it's cumbersome and annoying, and you don't want to do that. So you really want to know at least the first derivative. So if you know at a given point also the first derivative, then you can move along that derivative. And that's great, and that's called gradient descent, and it's already much better. Ideally, you would also like to know the Hessian, or the second derivative, because with the Hessian and the first derivative, you basically have a second order Taylor series expansion. In other words, you have a quadratic model, and you can just go to the minimum of your quadratic. And that's, of course, Newton's method, and it's even faster. It's way faster than gradient descent. As you'll see, we'll be somewhere in between the first and the second derivative, and I'll explain that in a second. Now, one other thing I should say is, of course, that this gradient will give you a direction, or this Newton's direction, Newton minimization will give you some heuristic point. But in practice, your quadratic model may not be completely accurate, because this is just a local model constructed from the first and second derivatives. And once you take a finite step, you might find that the function actually behaves very differently. So what people do in practice, and that's also what we did, is you just augment this with the line search methods. So you say, let the gradient, or the Newton minimization, the minimization of the quadratic model, let's just consider the direction given by what I sketched here as the green arrow, and then we'll just try to take a step, the Newton step, or a gradient descent step. And if that doesn't quite work, we'll just, I mean, we could in principle start exploring all kinds of other directions, but that's very hard. So we'll just start moving along this line given by the Newton direction. And we'll just try to backtrack a little bit if our function is too big, or try to go forward a little bit if the function is too small. Generally, people only backtrack, actually, until you find a point where you say, okay, here my quadratic model was reasonably accurate. The function is decreasing a little bit. Let me just accept that point. Take a step, compute the gradient, compute maybe the second derivative, and start and repeat the procedure. So in practice, what we'll do is something in between gradient descent and Newton's method, together with the line search, to get an acceptable next point. I have some words about how to say, so how do we compute this gradient? The gradient is hugely important. We want to compute it. Every point, the navigator function evaluation is a semi-definite optimization, semi-definite program. So an optimization semi-definite program. And so we would like to know what the derivative is. Now, in principle, you can do that with finite differences, but you can also, in fact, compute the derivative extremely cheaply. So the question is, what happens to a semi-definite program at optimality if you change the parameters a little bit? And so I have in parentheses, so here's an open parenthesis, and there will be a closed parenthesis in a few slides. Some notes about how to compute the gradient of a semi-definite program. So an SDP gradient formula, which is also something we wrote about in the paper. So this subsection consists of 3 parts. I'd first like to briefly recall semi-definite programming. That'll be very, very brief, but just for the people who are not completely in the know. Then I'll introduce some Lagrangian or Lagrange function, and then we'll find the gradient formula from that. So the recall of semi-definite programming, apologies to those who know this, which may be the bulk of you. What we want to do is we often want to maximize the coefficients. Well, we have as our freedom some vector of coefficients that I call typically called y, and we want to maximize bt.y, where bt is given, subject to some constraints of positivity of the functional for. Here I did it for all delta. In practice, it's only delta above the unitarity bound, but that doesn't change much. But the constraints are basically something like this. So the normalization allows you to extract a constant component, c of delta, and then you have a linear combination of y's with some function b of delta. And you want to pick the y's such that this coefficient is positive, this function of delta is positive for all delta. And in practice, we use a polynomial approximation. So these c's and b's are polynomial in delta. But if a polynomial is positive for all delta, then it's just, this is an elementary fact of polynomials in a single variable. It's just the sum of squares. You can write it always as sum of squared polynomials. And a polynomial, of course, I can write it as like this, right? You take a vector of monomials, 1 delta, delta squared, and so on. And then you take the vector of coefficients. And this inner product will give you a polynomial. So my sum of squares polynomial looks like this. I have the vector of monomials, the vector of monomials transpose, and then in between I have this, this outer product of the vectors of coefficients, summed over all the different terms in this sum of squares. But this, of course, is a product of rank 1 matrices. And so I can also say that this is a sum of monomials times the matrix P, sum of monomials transpose, where P is positive semi-definite. And in fact, it also works the other way. If you can write it like so, then you can see immediately that this function is positive. So that leads me to this, where you say you maximize this over some, you find some coefficient y such that this is maximal and such that this guy can be written as like so, where P is positive semi-definite. So this is where positive semi-definite is coming. But polynomial inequality is, of course, inequality between polynomials, where you just check it at degree plus 1 points, which I call delta n. So when I evaluate this guy at a given delta n, I just write it with the subscript n. So this is now the problem. Max bt.y such that cn minus yt.bn is equal to, it's typically written like this, trace an.y, but the an are just these vectors of the outer products of these vectors of monomial. And then y is, I renamed the matrix P as y, and y is so positive semi-definite. And y is the traditional notation in our literature, so that's why I call it like that. So here's then our semi-definite programming problem. I dropped the indices a little bit, but it's still the same idea. bt.y such that c minus by equals trace a star y. And so the index n is dropped from cn, bn, and an. But you can think of them as vectors in this space labeled by this index n. So now we want to change the parameters a little bit. We change, in particular, little b, little c, and capital B a little bit. This is where the parameters of the semi-definite of the original Bootstrap problem enter in the semi-definite program. So what is the first derivative of this maximum under a change of little b, little c, and capital B? So to find that, let me introduce, so the answer here is at the bottom. Let me first jump to the answer, and then let me say where it comes from. So the variation of this optimization program under a change of little b, capital B, and little c is given as follows. Little b.y, little c, the change in little b.y, change in little c.x, and then this product. So interestingly, what does not enter is the variation of y with respect to b, right? Y could in principle change, and x could change, well, x, oh, I haven't introduced x yet. It'll be there in a second. But the variation of y does not enter. And that's what makes this gradient formula really nice, because y, the computation of y, little y and capital Y is a big problem. But here we see that in the gradient formula, these variations don't end. And so that's why this formula is so nice, because you can just take your output of your semi-definite program and then immediately evaluate the gradient. So where does this formula come from and what are these x's? Well, that comes about as follows. So you have a Lagrangian that I introduce, which has minus the thing to maximize. So this is now the thing to minimize. And then the constraints with some Lagrange multipliers x. And then I want, for this positive semi-definite condition, I introduce a so-called logarithmic barrier function for the determinant of y. So of course, this function looks like this, where nu is some positive constant. And it goes to infinity. And you should think of the function as being infinity when the matrix is not positive semi-definite. So it looks a bit like this. And so if you start to numerically minimize this guy, this barrier function will prevent you from stepping outside the space of positive semi-definite matrices. So the idea is always that you start with y positive and you step around, and y will never become negative. And this barrier function will push you out of the bad region. Now, suppose I optimize this Lagrangian, I numerically find an optimum point such that the gradient of this, or the variation of this Lagrangian is 0. So I call it y star, with big y star, little y star, and little x star. So the x star are the Lagrange multipliers, and little y and big Y are the same as in our original problem. Of course, this thing will depend on nu, so that's why there's a subscript nu here. Now I make 3 claims. First of all, if you have found this optimum where capital Y is positive because of this positive semi-definite because of this barrier function, then I can take the limit as nu goes to 0. And first of all, my claim is that this exists and it solves this problem. So the barrier function was important in intermediate stages, but if you send the barrier function to 0, of course, if you take the limit, it still remembers the existence of the barrier. And then you will find a solution to the original problem. Second, if I plug these values that I found, x star, y star, and capital Y star into the Lagrangian, then I get the objective of the problem. I get bt dot y up to a minus sign in the limit as nu goes to 0. So what happens in the limit as nu goes to 0? Well, by optimality, these x's are Lagrange multipliers, so this whole constraint business vanishes. Then there's this bt dot y, which is the term I want. And so what I'm really saying is that this term vanishes, the term corresponding to the barrier function. Now, what happens in practice if I send mu to 0 is you say, oh, it may vanish. But actually, the determinant of y can become singular. But we can show that this is just an extra term that's basically of the order log of nu. And so you get a new log nu term. And so the non-trivial statement is the non-trivial claim is that this thing vanishes and nu log nu goes to 0 as nu goes to 0. And so your Lagrangian goes to the objective. So this is, of course, very promising, right? Because now you're at a stationary point in the Lagrangian, and you just take the value of the Lagrangian at the stationarity, and that's your objective. So, and we all know that if you vary the Lagrangian, the parameters in the Lagrangian around the stationary point, then you can just, to first order, plug in the old solution in the new Lagrangian. And that's very nice. And the only non-trivial claim is that this procedure commutes with the limit, taking the limit as nu goes to 0. So if you want to vary the original problem with respect to parameters in the original problem, then of course I can say, well, the original problem is just the value of the Lagrangian in the limit, but I claim that you can swap taking the limit and doing the variation. And so you can vary the stationary Lagrangian and then take the limit. And varying the stationary Lagrangian doesn't involve varying x star, y star, and capital Y star to first order. And so you're done. So that is the reason for this SDP gradient formula. Right. So this is a bit of a technical thing, but we're of course in the parentheses, so it's not super important for the rest. It's just important to remember that we can take the gradient of the Navigator function very, very cheaply. Computing this little b, little c, and capital B is easy. Finding this y and capital Y was the hard part. Now, what about the x? I haven't told you what the x is. The x doesn't sit in the original problem. And they're basically Lagrange multipliers in my Lagrange formulation. But fortunately, in SDPB, our standard program, we actually also compute the x's. And this is a general feature of primal dual optimization algorithm. So as it happens, if we do the numerics, we compute not just little y and capital Y, we also get the x's. And so this is really an extremely cheap algorithm. You don't have to run SDPB again, you just get the gradient. Of course, interesting question would be if we can make it even cheaper, and that would mean would involve computing a little bit faster these variations of little b and little c and capital B. But we haven't. Well, you could see that as a problem for the future. At the moment, it's not the bottleneck, computation. I should say we've also found a nice formula for the Hessian, which is basically the variation of the variation. And it looks like this. So you just see that there's some delta y's and delta x's involved. But in practice, even computing those is not so hard. It's of the order of one SDPB iteration, up to some subtleties that I'm not going to delve into. So we haven't used this Hessian in our paper, but in principle, you could use the Hessian, the matrix of second derivatives also. And finally, I want to say, I want to stress that even though we have a nice SDP gradient formula, I don't think this is a proof of differentiability, because it is not entirely guaranteed. This Lagrangian is nicely smooth at its extremum. So I think there could be cases where the navigator function is not. Well, I'm pretty sure there could be cases where it's not C2. I think there could very well also be cases where it's not even C1 differentiable. But of course, in practice, we've seen that it worked very well and it was very differentiable in the plots that I just showed you. So that was the parentheses that closed here. And so we know the derivative. Long story short, we know the derivative of the navigator function. So we can go back to navigating. We have a point, we know the gradient, and we can choose the next point and so on and so on. Now I have to go back to this idea that we're sort of in between the first and second order method, the gradient descent and Newton method. So the algorithm we used is very well known in numerical optimization. We really took a Python library and basically used it with very minimal modifications. So it's called the Bfgs method, named after 4 people whose names I unfortunately forgot, but you can find it on Wikipedia. It's a very famous method. And the idea is to minimize a quadratic model that's not exactly based on the Hessian, but it's a sort of a quasi-Newton method. So the idea in particular is to estimate the Hessian as follows. So you have taken a bunch of steps, and you can say, well, my Hessian at the k+1 point, I can try to estimate it by finite differences from the previous point. So I take the gradients, the difference in the gradients between my last 2 points, and the difference in positions, and then the Hessian should, in principle, if the points are sufficiently close, should look like this. And in practice, this is not a terrible approximation at all. It works very well. Of course, this doesn't completely determine the matrix of second derivative. This is a matrix of undetermined symmetric matrix. This is just a vector of equations. So what the Bfgs method proposes is to do some kind of update from your previous Hessian with some rank 2 update. So you take the outer product of 2 vectors u and v that are chosen such that u is the difference in the gradient, v is Hessian, the previous Hessian times the difference, the step that you took. So this is just nice, and you can pick these coefficients such that this equation is obeyed. And the initial Hessian is typically taken to be the identity, because initially you really have no idea about the Hessian. Now, as I said before, you refine this with the line search. And then this, in a nutshell, is the Bfgs method. So we did only minor modifications. We imposed the bounding box. So we said, well, the line search should terminate at some point because we don't want to go to the continent. We want to stick to the island. So we imposed this bounding box. We were slightly smarter in picking H0 because we know a little bit more. And of course, our termination criterion is very different. If you just want to find a feasible point, we can stop as soon as the navigator function is negative. We don't have to go all the way to the minimum. The Bfgs method is really aims to optimize, find the minimum. But in this case, or that's sort of where it really shines. But in this case, we found that it's totally adequate. Also, if you just want to find the point where the navigator function is negative. So to recap, this is the workflow we now propose. We have a navigator function, which was the minimization of this mu parameter, which shows the coefficient of this extra term in the crossing equation. We have an SDP gradient formula to get the gradient of the navigator function. We use the Bfgs algorithm with our minor modifications, so Bfgs prime minimization algorithm, to navigate towards a point where an island where the navigator function is negative. So the question is, does it work? Can it work at all? So I can provide you with a log of our travels towards the easing islands in particular, where for the experts, we looked at easing island with lambda equals 11 and lambda equals 9 mostly. So this is really just a test case to see if the navigator function works and allows us to find the island. So that brings me to the last part. Let me again pause here and see if there are questions. No. Okay, so here we go. Here's an example of a two-dimensional search because it's nice to plot. So we have the easing island here on the right. We have the same navigator function as before, and we just unleashed our Bfgs algorithm on this function. We started here, randomly chosen point. We step towards point 2. At point 2, we compute the gradient, we update the Hessian, and we try to go to point 3, which I think was somewhere here. Then 4 is there, 5 and 6. So what happens here? Now these points 3, 4, 5, and 6, they all lie along a line. And this is the line search in action. So the updated Hessian will tell you that I think you're supposed to. So maybe 3 was a red point. Okay, the updated Hessian at some point tells you to jump to point 3, say, but the function doesn't decrease at all there or doesn't decrease enough. And the model thinks, okay, my model is probably wrong. My quadratic model with Bfgs Hessian is probably wrong. So I'll just search along the line provided by the search direction. And what you'll see, it just jumps around 4, 5, 6, 7, 8, 9, all the way up to point 14, I think. And point 14 was accepted by the line search. And so then it does the next step. So this is a red point. It's a Bfgs step. And the blue points are line search trial points. So that's how you get this pattern. And then from 14, it took a step which was way off. It went to 15. And I was like, no, that's bad. So it goes back 16. And then it accepts that point. And 16 to 21 are basically in the here, I think. And after every red point, it updates the Hessian. It starts a new line search based on the Newton search direction and so on. And you see that the model for the Hessian, so you see what this function has is a very narrow value, and that just takes time. I think this is unavoidable. But you see the Hessian estimates improve because you have a lot of blue points at the beginning. But at some point here, 25, 26, 27, 28, 29, these are all red points. So here the Hessian, the quadratic model seemed to be accurate because every step was accepted by the line search. And this is very typical for Bfgs algorithms. So the model just performs better and better the more iterations you have. And it took us 29 steps here to find a feasible point where the navigator's function is negative. This was slightly longer than usual. And we've done a bunch of these runs, and in this case, it took about 19 steps normally. And then we continued to see if we could also find the minimum of the navigator function, because why not? And it took us 66 steps to get to a step size that was so small that we declared it to be converged 10 to the -8, which is reasonably normal, which is not entirely crazy. So this is just to show that how the Bfgs algorithm works and that can be used for our navigator function. Now, of course, as I said, for easing, there are 3 parameters. So here's a 3-dimensional search, delta sigma, delta epsilon, and on the vertical axis theta. We started with 20 points. They're the black points. we ran our algorithm, and nicely enough, almost all of them converged to this easing island that you cannot even see. That's this very small island here. And they all found, or almost all of them found this negative point eventually. So this is the full size space in which we search. So this is the full bounding box shown. In practice, it took each of these points about 50 steps to reach a negative point. You see there's some three-dimensional analog, I think, of this valley, right? Where all the points sort of try to cluster along this line. It seems to be some kind of three-dimensional valley. I must say there are some failed runs. So a failed run can happen like here, this one on the right. It took one step, and then the next step was outside the bounding box. And you can try to correct for that, but as long as, so what it found is that here it really wants to go to the other minimum. It wants to go to the continent. And so at this point we declare the run to be failed and we just give up. So this is a thing that could happen, and in practice you would have to pay attention to failed runs. So in this case, it happened that I think this is another failed run. It also points out to them steps. So these were the only two that failed. So here are some further details of the search. I'm a little bit out of time, but let's just look at the first one. I plot the value of the navigator function, and I plot the value of the kth point, or its distance to the final point. Red points are again accepted, and the blue points are the line search points. And you see when this is a log plot, so when the navigator function is negative, we stop. So that was here after the 50th iteration. So I drew this line here. It should be about here after the 50th iteration. It stops, and then we can plot the difference. But on this plot we didn't plot the navigator function. And you see some nice convergence. It's all totally in line, well, more or less in line with expectations. So for those who don't know about numerical optimization, maybe it's useful to recall that for gradient descent, you would have linear convergence, which on a log plot would mean a straight line. And if you would do a proper Newton's method, you would have quadratic convergence, which on a log plot would mean a parabola. And here, I mean, you have to estimate it numerically, but I'd say it's definitely superlinear. And superlinear is exactly what you should get with the standard Bfgs algorithm, according to the textbooks. So that just goes to say that I think this navigator function works in this case, and it does more or less exactly what you expect it to do. Now, as one slightly different application, and this is almost my last slide, I want to say that you can also use the navigator function very, very easily to find the tip of the island. I started in the beginning with this idea that you want to project down to one dimension to write your abstract, at least of the paper. And so that means something like this, right? You want to say maximize the scaling dimension, for example, delta sigma, such that the navigator function is negative or maybe non-positive, so less than or equal to 0. So that is also actually a fairly standard optimization algorithm that you can attack in all kinds of ways. And we have a particularly, well, we have one particular algorithm that I like. It's kind of a homegrown algorithm. It's not as well developed as Bfgs. There might be others, but this one works well enough, I think. It's based on Bfgs to get the Hessian, and then there's some smart way of stepping around that's based on introducing Lagrange multipliers for this constraint here. So it's a Bfgs-based algorithm. You can read the details in the paper. It's again based on this quadratic model of the function that you naturally get in Bfgs. And as you can see, so here, I think the convergence is really, really great. So you start at some point in the island. You didn't even have to do that. You could have started somewhere outside the island. And you step around, and very, very quickly, it just moves into the right direction here. And then here in the zoomed in plot, you see that the precision gets insanely good compared to say bisection already after 10 or 12 steps. And then the rest, I mean, that's just for fun. You can get, in this particular case, we could get this optimum to 10 to the minus 30 accuracy extremely easily. It took like 17 or so runs. So this is literally The accuracy, of course, of this point is the error bar on your error bar, because this is going to be the upper allowed value of delta sigma, so that's your window in which delta sigma lives, and that upper allowed value can be determined much more accurately than you ever wanted to know it. And you should compare this to the bisection algorithm, right? The bisection, you would have a crude picture of the island that you would map out with points. As I said, you zoom in and you see that this blue contour is made out of a bunch of points, allowed and disallowed. And what we did here is that you see that to carefully map out this boundary, we had to do bisection for, I don't know, I think it was a few hundred points here. The black points are the ones that are allowed, they're inside the island. The red points are the ones that are not allowed. And this blue contour here is really just a line that passes in between all the red and black points. So that's how you determine this island in practice. So our proposal here, of course, would be to do away with the finding of this blue region and to just use our optimization algorithm that tells you the maximal value delta sigma immediately. And you can see, I mean, there was hot starting, and so you can say, okay, finding each one of these red and black points takes less time than our algorithm. But you see that the scaling is such that our algorithm wins. Once you start playing this game in a 13-dimensional space, you're completely out of luck. This just becomes impossible. And with our algorithm, I think with the navigator function, I think it might be completely possible to find these max and min allowed values of the scaling dimensions, or other things like OP coefficients. So this is then a summary and the last slide for my talk. We propose to use this navigator function to this type of navigator function where you minimize this coefficient mu that I talked about. We say you should use the SDP gradient formula to get the gradient of the navigator function, maybe a Bfgs algorithm, or maybe a Newton algorithm if you really want to use the Hessian also, to minimization algorithm to start navigating in parameter space. And this will allow you to find points where the navigator's function is negative, so points inside the island. It will allow you to find the tip of an island, and it'll probably allow you many other things that we haven't even thought about that would require, in principle, the navigating around in these parameter spaces. So let me end here. Thank you very much.
Thank you, Balt. Any other questions?
So I have a very naive question. I'm not an expert, so sorry. So, well, so I would think that ultimately what you want is that your island is not actually an island, but a point. And so the first naive question is, what determines the size of this island in your method? Is it this capital lambda that was not explained, or
yes,
just the number of correlators that you're looking at, bootstrapping and so on?
Yeah, both. It is how hard you let the computer work.
But how do you improve? What do you add to improve?
So here's a crossing equation, and this is an equation I wrote Z and Z bar here, but of course these functions f and the identity operator, the conformal blocks, they also depend on Z and Z bar. And so what we do, I think, as Alessandro explained, is you you take derivative of this crossing equation. So I can just take more and more and more derivatives, and then I have more and more constraints to work with, and I can get better and better bounds, better and smaller islands. But this is just one crossing equation, so I can throw other crossing equations in the mix. I can say take 3 different 4-point functions, and for each of these 4-point functions, I have crossing equations, and for each of these crossing equations, I take 20 derivatives. Or, right, you throw in more 4-point functions, you throw in more derivatives.
And that grows the dimension of your parameter space, right? So
yeah,
that becomes, okay. But okay, I have a less naive question, I guess. So suppose you fix these numbers and you work with a specific island which has a finite size, but is there any reason to believe that the actual minimum of the navigator function is closer to the actual point you're looking for? Then I mean, maybe this is a better estimate than...
Yes. That is definitely a less naive question, and it is something I thought about including in the talk. We did find the minimum of the navigator function, and I don't think we have a. We went all the way to roughly speaking, determine a minimum. And it turns out we actually, for this particular case, have much more precise data. Sorry, it may not be exactly this search, but roughly speaking, we have much more precise data. And the minimum of the navigator was within 10% compared to the size of the island of the much more precise result. So yeah, it turns out experimentally that the minimum of the navigator function that we used here was reasonably close to the more precise.
Maybe you can sort of do a cheap search with a smaller parameter space first, and then use this result to determine the starting box for the more expensive search.
Yes. Yeah. These are definitely things that we can that one can explore. Absolutely, I think this might be something worth looking at. So I think it'll never be completely perfect, because the minimum, of course, depends on the choice of this function m, and this function m was chosen a little bit arbitrarily. So there might be functions m for which in certain problems it works better. There might be other certain functions for which it works worse. And so I don't think there's a guarantee that the minimum of a navigator at some value of lambda will be the best predictor for the allowed value at very high lambda. But yeah, as a crude guess, it may be very useful. Yeah.
Thank you.
Anything else?
Hi, Balt. I had a wildly speculative question. Can any of you guys envision something where this navigator function has some sort of, or at least it's related to some sort of physical quantity that you might hope is like telling you how you move around this theory space? It's kind of like a weird constrained version. I don't know, but you might imagine that it's related to something like RG, or like in 2D, it's like this. You might guess that there's some C functional and it's related to something like that. But you guys are doing something weird, like from that perspective, you're sort of using conformal representation theory, but you're sort of relaxing that the OP associativity is satisfied. So it's kind of some carefully chosen way of relaxing the problem that allows you to move away from the CFD point, but you're still floating around in theory space.
Yeah, it would be cool, I think, to have a more physical picture. I was already happy we found these functions. Maybe my collaborators have smarter things to say about it, but at the moment, I think I don't have a way of making this more physical, but maybe that's just me.
Thank you.
We have various speculations in the paper, but I don't think we have any speculations on this. I think this field for speculations is wide open, right?
Are there any further questions?
I have a question. In the island for the Ising model, what is the minimal value for the navigator? Is it of order 1 still?
Yeah, I think so. I don't know. It's probably, I forgot.
Oh, it's not it's not order 1. It's like 10 to the minus whatever, very small. Well, Martin wants to say what it is.
No, I want to say something else. Exactly, it's very small, but let's say 10 to the minus 3 or 10 to the minus 4.
Oh, I see.
Maybe depends on the exact lambda, and yeah, small, that order, that range. 10 to the minus 4, maybe 10 to the minus 6 if you increase lambda.
Okay, thanks. Just curious.
Okay, there's nothing else. We can thank Balt again. See you next week.
Thanks, guys.